In case you can't see me, this is Colin Jones speaking at the moment. This is the second online UKESM General Assembly. This is 2021. It's today and tomorrow. I want to welcome everyone to it. I wish we could have it in person, and who knows, maybe in 2022 that wish might be granted. But for now, we're just cracking on as is here. Before I start, I want to thank Hazel for doing most of the preparatory work for this. We'll thank her again at the end. So I'm going to crack on a little bit. We've got an hour of sort of plenary session. Hazel, could you go to the next slide, please? Thinking if I need to move forwards. So just quickly, the agenda for today is we have an hour of sort of us giving you some updated information, then a short break. Then we'll have a little bit of a plenary discussion about one of the topics for our one-year extension, which is about developing some workshops. Then we have a lunch break, and at 1:45 we'll come back and we'll have some breakout groups, 2 sets of breakout groups, and we'll mention those as we go along. Next slide, please. And then tomorrow we have a little bit of a report back from the breakout group, but primarily tomorrow will just be science presentations from all of you guys that are in the project, and we look forward to that. Okay, next one again, please, Hazel. I'm going to go rapid fire here. So just as a remember, and I'll mention this in a little bit to come, we have 4 breakout groups. So today, today at 12:45 to 13:30, there's 2 groups. One, observational constraints on historical Earth system change, and the other, analyzing future Earth system changes and risks. So please, if you haven't decided which, then decide which you're going to go to, and make sure that you go via the right Zoom link. See the bottom there for instructions. I should say that the A and C ones have slightly less people registered than the B and D. So if you are unsure, please favour A and C, so we have some decent numbers in each. After the break, we have follow-up ones, where one is evaluating historical simulations and the other is about analysing feedbacks and methodologies for analysing future feedbacks. And you can see there's a chair and a co-chair for each of those. So please go to one of the breakout groups at the relevant time. Okay, on again, please, Hazel. Okay, so a brief bit about the one-year extension. You remember that we wrote something asking for this one-year extension, and we have been writing something, a number of you will know, for the subsequent 5-year project. But this is the one-year extension running from April 2021 to March 2022. Next one, please, Hazel. We have 3 topics nominally that we're addressing in this extension. We call them research areas for RA. One is understanding historical radiative forcing and historical Earth system change to increase our confidence in future projections. 2 is about analysing future projections, analysing future Earth system change, and maybe trying to say something about the impact of that. And the 3rd topic was about support for the UK user community, and also developing some new collaborations, which we'll talk about shortly. Yes, thank you, Ranjini, for reminding me. So Ranjini is asking that you post your questions into the chat. And as we've got a number of different speakers in this first hour, if you can indicate which speaker your question is for, then Ranjini will organise them and ask them at the end of the 1-hour session. Okay, next slide, Hazel, please. Okay, so just touching a little bit on RA1, I'm just going to really this is more than anything a motivation for the breakout groups afterwards. So RA1, what we thought there was, not exclusively, but one topic would be to try and develop a set of observational constraints that could help us to understand and evaluate and constrain the historical performance of our own models. So that's UKESM 1, UKESM 1.1 you'll hear about later today as a new configuration, and UKESM 2 is our future configuration. But to constrain any model simulation really of the historical past, which is something over the period 1850 to present day. We started thinking about this for constraining parameters that control historical surface temperature evolution, but that isn't the only thing we might want to think about. But the list I've got there are examples of things that you might use to constrain things that influence the historical surface temperature evolution. So I've just listed a few. Sulfur dioxide and SO4 concentrations. These can be observed both by satellite, but particularly at station data. And they're pretty strongly linked to aerosol radiative forcing. So they're quite strongly linked to one of the important drivers of warming or cooling over the historical period. Then we might want to think about surface and trends in top of atmosphere, solar radiation, and possibly even outgoing long-wave radiation. Again, these are partly linked to aerosol forcing and they're partly linked to cloud reduction. And I've put cloud trends in the third bullet. Our model, if you know that, probably has post-1990 a relatively strong reduction in cloud amount, which drives an increase in surface radiation, which is the primary driver of the warming over that period. And that is kind of a shortwave cloud feedback in action during the historical period. It's what drives the high climate sensitivity in our models. And we don't know whether it's right, wrong, too big, too small, but we have a relatively high positive shortwave cloud feedback in the abrupt 4 times CO2 and the 1% CO2 runs. So could we evaluate some of that in the historical period? Possibly. It might be difficult because the trends are not that enormous. Then we have trends in ocean heat uptake. Ocean heat uptake is a very good surrogate for top of atmosphere net radiative forcing, so that's worth thinking about. Trends in Arctic sea ice and even trends in surface temperature itself, taking them in different ways. So for example, looking at the trend in northern hemisphere versus southern hemisphere temperatures, which again can manifest some aspect of aerosol forcing. Okay, next slide, please. And then, of course, we're not just thinking about surface temperature, although that is very important. So what about other variables? So I just listed them. And then as I listed them, I realized some of these are probably already covered. So there are key marine, physical, and biogeochemical parameters. Andrew has written a paper on UKESM historical performance. So the updated models may not be sufficiently changed to warrant an updated parameter, an updated publication. But at least we could gather together what we think are the main observational constraints, maybe. Same for vegetation type and extent, because we predict vegetation type and extent, but also for other, of course, other important land use, land properties like soil moisture, soil temperature, snow cover. So some of these might be covered in the paper that Doug's putting together, but it may be that we can extend and we can think about, in particular observations. I just wrote there one aspect might be to think about ENSO and its driving of Amazon. And then likewise for ice sheet parameters, we might ask, what can we talk about for the historical period? And is there something that we can say about historical evolution? Certainly sea level is a very important component. Again, they may already be covered. Then we have other parameters coming into our models. Fires is one example that will come into UKESM 2. So should we think about running offline simulations with our simulated historical climatology to look at fire evolution? And then there are other areas that we might want to evaluate, like the chemistry or other aspects of the physical climate parameters, so cloud droplet number, precipitation, etc. And then I highlight modes of variability as well. And so Pacific decadal oscillation, Atlantic meridional oscillation. These are things that we might want to evaluate, and then we might want to look at how they change as we go into the future. So for the 1-year extension, we've got one paper on the go already about UKESM 1.1, which Jane's going to talk more about in a minute. We hope to maybe get this one paper on how we could best use observations to help constrain the simulation of surface temperature and the drivers of it, and then possibly one further paper on one aspect of historical performance. And if we got to that level, I think in the 1-year extension, we would be pretty happy. Okay, next slide, please. RA2, I'm not going to say too much about this one, analysing future Earth and change and its socioeconomic impacts. We've started doing this in the context of looking at changes at different levels of global warming. It's obviously not the only way you can do that. Ranjini will give a presentation tomorrow of one paper that's in review at the moment where we've done that. You can obviously look in other forms. You can look in the time axis as well, and you can look as a function of different emission pathway into the future. Some of the things we've talked about, and I'd encourage you to talk about more in the breakout group, are how can we continue this first paper? So should we be looking at different areas of the world, maybe the Amazon or maybe tropical forests in general, possibly for the Amazon or tropical forests, linking them to changes in ENSO. We could look at what I've called subtropical drying regions, so I'm bracketing the Mediterranean, Central America, Southern Africa into that category. Or we might want to look at changes in the Northern Hemisphere, subarctic and the Arctic as well. Or we might want to look at things in terms of certain phenomena, so changes in drought frequency, drought intensity, or changes in intense rainfall, or changes in hot and dry periods. And one of the things I think we do need to do is extend to a multi-model analysis. So go beyond just our own model, but bring in the full ScenarioMIP ensemble. Next slide, please. I think I'm nearly done. So the breakout groups are really around these RA1 and RA2, as you can see. So A and C are very much around RA1, and B and D are very much around RA2. So again, what the aim would be to try and identify a couple of papers that we can genuinely realize during the 1-year extension period. Okay, so those are the breakout groups again. Next slide, please. My last one, I think. And that is RA3. And RA3 we're going to talk about in one portion of it after the first break. So RA3 is about supporting the user community. So that means the users of our model. So Jeremy is porting UKESM 1.1 to Archer now, Archer 2. So it's about continuing to support users of our model and users of the tools, like ESM Val tool. Then within RA3, we also talked about some new collaborations. And we suggested we'd organise 2 workshops in the 1-year period. One where we talk more with the climate impacts community in the UK and try and build some bridges to get them actively using our simulations and for us to know a little bit more about what their needs are from our data. And a second with climate policymakers, so particularly here we're thinking of government departments, but not exclusively. And one option there might be that these discussions could begin to be a planning aspect for terra firma. And those of you that are not clear what terra firma is the new proposal we just put in for a 5-year new project, which wouldn't be UKESM 2, but one part of it would be UKESM 2. So after the break, we have a plenary on this where we'll just try and throw around some ideas on these 2 workshops. And I encourage you to bring any suggestions and comments to that one, please. Okay, next slide, and I think this is me to hand over now. Handing over to Jane. Are you there, Jane?
Thanks, Colin.
Okay,
yeah,
I shall mute.
Hopefully you can hear me. Hello, everybody. Sorry, I'm keeping my video off to save on my bandwidth, so hopefully you can hear me all right. My internet connection isn't super fast here. So I'm just going to give you an update on UKESM 1.1 activities over the past year. So this is obviously not just me, but a whole list of people listed here on the slide have contributed hugely over the past year since our last meeting. And in fact, I was trying to chase the slides I gave at last year's General Assembly to kind of remind myself of where we were last year, this time last year, and what we've done since. And so we've got quite a nice set of results, I think, to share with you now. And we've done a huge number of simulations. So this is going to be a very rapid, quickfire summary of that work. So just a little reminder here in terms of the plot, in terms of the motivation for UKESM 1.1. Hopefully, you won't be able to see my cursor, so I'll just describe it carefully, but you'll see the motivation for UKESM 1.1 was obviously, the large cold bias in the mid to the end of the last century, and we were looking at ways of improving the model to subsequently lead to improvements in this large cold bias in UKESM 1. So this is showing the temperature anomaly time series with respect to a number of different observations, Hadcroft 4 and the Cowton and Way data set. So next slide, please, Hazel. Thank you. So again, this is a reminder. I presented this slide last year. So I think at this point last year, we had pretty much frozen the science that we wanted to get into the model, and so the primary science that improvements that went in there were changes to the SO2 dry deposition. So in there we corrected a bug that we found in the UKESM configuration in the SO2 dry deposition, and we also introduced a new parameterization to account for the surface wetness, which has obviously, in terms of SO2 being highly soluble, this has a significant impact in terms of the near surface deposition. So I think we discussed a lot of that last year. Also, that went in, there was a number of other bug fixes. You can see here in the red box, they mainly actually relate to UKCA, so chemistry and aerosol bug fixes that came to light, I guess, after UKESM 1 was frozen, and another smaller fix to the couple CI heat fluxes in NEMO. And then we used the opportunity of developing a new configuration then to revise some of the tunings that, with the benefit of hindsight and the evaluation activities we've conducted on UKESM 1, we could re-look at these tunings that were largely explored in Alistair Sellers' UKESM 1 documentation paper. So we revised the albedo of snow on sea ice, as well as the burial of vegetation by snow. We've retuned the dust, and we've also looked at things like the QBO, which we actually neglected to tune in UKESM 1. And then obviously there's just the final tunings of the TOA at the end when we were finalizing the configuration. Next slide, please, Hazel. So again, this is another just reminder in terms of the main science change that went into UKESM 1.1, and that's the SO2 dry deposition changes. So this is a figure from Catherine Hardaker's paper, which is now under review in ACPD. And again, showing the UKESM 1 configuration here in blue. And then in the red, we have the UKESM 1 with just this is not the 1.1 configuration, but it's just got the SO2 changes in it. And you can see at these a number of ground-based measurement sites. I think we were using the CASNet data in the US and the AMIP data sets over Europe, and looking at this time series from the late 80s to, I think that's about 2015. You can see that UKESM 1 showed a very large positive bias in the SO2, which has largely been reduced by half with the new SO2 deposition changes. Looking at the SO4 in the bottom row, you can see obviously we do actually have at these sites in Europe and the US actually a low bias in the SO4. So this isn't the complete picture in solving the sulfur cycle, but it certainly seems to have a large impact in terms of the amount of SO2 that's then transported away from source, in terms of the amount of forcing over the kind of remote marine regions. Next slide, please, Hazel. So since the last, so they were just kind of literally just a little bit of a reminder in terms of what UKESM 1.1 is. And really what we've done over the past year is finalized and fine-tuned that configuration. And we have run a number of simulations. So we've run a full set of deck simulations. So we've got 6 historical members. I guess I should start with the PI control of the final configuration. We have over 450 years, but that's suffice to say that actually preceding that, in the development of the model, we have another probably 400 to 500 years of PI control. So we have a very long PI control. I think at the point last year, our initial historical simulations were showing that perhaps these changes weren't having as large an impact on the temperature bias as we expected, but we now actually believe that we actually just hadn't a stable, our PI control at the time wasn't spun up enough and wasn't as stable as it is now. So I think I'll show you some updated results, which should highlight the impact of that. So as well as the PI control, 6 historical members, we have conducted the 1% CO2 runs, a 4 times CO2 run. We have also conducted a number of scenario simulations. So for now, we focused on the SSP 126 and 370 scenarios, and we've run for each of those scenarios, we've run 3 members. We've got the AMIP configuration. Currently, we're setting up and running a number of ERF, effective radiative forcing experiments, and so there we'll aim to focus on a kind of an RF-MIP light, kind of doing the tier 1 RF-MIP experiments. And as Colin already mentioned, this configuration is now currently being ported to Archer, and Archer 2, overcoming a number of technical hurdles, I believe, but that is certainly on the way. So the configuration is frozen and imminently due to be released to the wider community. So the plot on the right there is just showing the long PI control. So the red is the PI control of which the historicals were spun off, and the black actually is the original AW310, which was the UKESM PI control. So again, you can see that broadly they're exhibiting the same variability and stability as the UKESM PI control. Next slide, please, Hazel. So top level, what is the impact of this new configuration on the global mean surface temperature bias? So focusing on the top left, which is the global picture. So again, this is the same plot as I showed earlier. This is the temperature anomaly with respect to 1850 to 1900. And again, we're now comparing, so in each of the plots that I will show in the rest of the slides, UKESM 1.1, so the new configuration will be in red, and the UKESM 1 configuration is in blue, and we compare 6 members of each. So while UKESM 1, I think we had something like 19 historical members, here we're just comparing 6 members with 6. So again, you can see a significant improvement in the global mean surface temperature bias. So this cold bias is largely negated now with the red curve comparing to the observations in black. Okay, we're still warming a little bit too much, so the climate sensitivity is still leading to an excessive warming period towards the end of the historical period here, but this cold bias is very much improved throughout the late 20th century. And again, looking at the northern hemisphere extratropics on the right hand side, top right there, you can see that this is where the predominant signal and change is coming from, and there's less coming from the tropics and the southern hemisphere extratropics shown in the lower panel. Next slide, please, Hazel. Looking at some temperature trends here. So again, we've got the HADCRT5 data now in terms of the temperature trends for different periods. So the top row is showing the 40-year period from 1900 to 1940. The middle row is showing 1940 to 1980s period. And then the bottom panel is showing the 1980s to the 2014. And so these are the temperature trends for those 40-year periods. The left-hand column here is showing UKESM 1.1 minus UKESM 1 difference. So you can see in the early period, in the top row, the change is actually quite small, I would say, and a little bit noisy. And so again, you can see that UKESM 1.1 in the middle panel still isn't capturing maybe that that warming trend seen in the HADCRT5 data. But when you look to the middle row here, to the 1940s, 1980s, where that real cold bias was at its largest in UKESM 1, you can see that the UKESM 1.1 is showing a significantly more positive warming trend, which does act to improve that large cold bias.
Jane, you have 2 minutes left, Jane.
Okay, thanks, Hazel. I'll speed up. So, we can see that there's largely a big improvement here in the cold bias exhibited in the 40s to 80s period. And again, you can see in the later period then that temperature trend has almost reversed as aerosol emissions have decreased from the 80s to the early 2000s. And again, while we still have a too large warming trend in the middle bottom panel there, you can see that the cooling trend in the difference plot here is showing that we've actually improved, that those biases are going in the right direction. Next slide, please, Hazel. So I'll run through a number of slides here because I know I have too many slides. This slide set really is showing, we can come back to these in more detail maybe in the evaluation and breakout group later this afternoon, but really this plot plots here are looking at a number of the aerosol properties, so looking at the aerosol optical depth anomaly, cloud droplet number concentration, and effective radius. And again, showing that most of this change, we're seeing a reduction in those anomalies. So in terms of anomalies with aerosol optical depth, so you're getting a lower increase in aerosol optical depth, a lower increase in cloud droplet number concentration over the historical period, and a subsequently less negative change in effective radius of forcing. And again, that's dominated by the change in the northern extratropics. Next slide, please, Hazel. I'll skip over this because we can discuss this later in the evaluation breakout group. But again, it's really just highlighting that in terms of evaluation, the changes in aerosol optical depth are beneficial and improving our biases against both satellite and ground-based observations. Next slide, please, Hazel. Looking a little bit more, moving to the ocean. Again, we're looking at the ocean heat content here in the upper 700 meters. And again, here we're showing that actually in UKESM 1.1, it has a higher ocean heat uptake. You know, from you can see here, these anomalies are relative to 1970, I think. And so you can see that in the middle panel here, that UKESM 1.1 takes up more heat than UKESM 1, which is in better agreement with the observations. Next slide, please, Hazel. And other ocean circulation variables like the AMIP and the Drake Passage, again, very small changes here, but you can see a systematic reduction in terms of the AMIP here, which would be consistent with the change in aerosol forcing. But otherwise, largely, we don't see any great change in terms of ocean in terms of the ocean circulation variables we've looked at so far, but they'll be explored in more detail in the paper we're putting together. Next slide, please, Hazel. Sea ice, again here looking at the Arctic sea ice, this is again worth showing. Again, we've got a systematically warmer climate in UKESM 1.1, and this seems to have a beneficial impact on the Arctic sea ice. So again, UKESM 1.1 is in the red here, so this is looking at the sea ice extent in the top left. Again, comparing with observations in the dashed and kind of grey lines. And again, you can see here that while UKESM 1 had too large a sea ice extent throughout the historical period, this is now, particularly in the period of the observations, is in much better agreement. And the same goes for the sea ice volume in the bottom right. And I should say here, I haven't shown the Antarctic because we see actually a much smaller impact in terms of the Antarctic sea ice. Next slide, please, Hazel. Looking again at the ECS and the TCR from the 1% and 4 times CO2 runs, again, the key message here actually is that actually, even though we've you know, dramatically improved our cold bias in the historical period, actually the impact on the ECS and TCR is minimal. So you can see the headline numbers there on the left hand side are, you know, very, very similar between the two models, and probably that's largely because, of course, while we possibly expected maybe some of the snow burial and maybe some of the tunings in terms of the sea ice or the albedo of ice and snow to impact those feedbacks, it does seem to be on the global scale at least minimal. Next slide, please, Hazel. And again, yeah, just to finish up then, a quick look at some of the future projections and some of the SSPs we've been looking at. So again, here we're looking at the temperature anomalies with respect to, I think this was from a 1980 to kind of 2000 anomaly period. And you can see actually systematically here, while even though the ECS is looking quite similar, it does appear, these are very kind of early results, so we're still picking into the detail of these, but it does look like in terms of temperature on the left and precipitation on the right, that UKESM 1.1 warms marginally a little bit less actually in both of these scenarios, and again the precip anomaly is lower as well. So again, these are early results that we're just unpicking, but there does look to be a slightly reduced warming in the 1.1 configuration. Thanks, Hazel. Next slide. So that's just leads me to a summary. Sorry, that was very, very rapid, but just really to update you on where we are. This is all these results are being collated now into a top-level documentation and evaluation paper that we hope to submit in the coming months. And the model itself, hopefully, we shall be released on Archer 2 very, very soon as well. So really, it's just to give you an update on the range of simulations that are now available and some of the benefits really and the improved results we're seeing with this new configuration. Many thanks.
Hi everyone, I'm Mark Stringer and I'm going to give an update on the hybrid resolution model. So just a quick recap on what the hybrid resolution model is. So typically in a couple model, you'd have two main executables. You'd have an atmosphere executable, which would be UM, and an ocean executable. Now with the hybrid resolution, we introduce a third executable, which is another UM executable. So this is a schematic of the hybrid resolution model. So the green rectangle there is our high resolution UM, which we call senior, and we remove any computational expensive science from there, which in this case is UKCA. The purple rectangle is our low resolution UM, which we call junior, and we run all our science in there, including UKCA. The blue rectangle is the ocean executable. And the idea of the hybrid model is that we lock the physical atmosphere of junior to senior by passing across dynamical core fields from senior, remapping them using OASIS-free MCT onto junior's grid, and then overwriting the native fields in junior. In return, junior provides all the UKC output that's needed by senior. So the ocean provides input to both senior and junior, but it only receives input from senior. So all the coupling is done with OASIS-free MCT along with a remapping, and we're running a low resolution hybrid, which is an N96 Senior with an N48 Jnr and an Orca 1 Ocean, and a high resolution hybrid, which is an N216 Senior, an N96 Jnr and an Orca 025 Ocean. And this configuration is, even for the same resources, this configuration is 65% faster than running all the sites at the high seniors resolution. Next slide, please, Hazel. So we're just in the process of tuning the hybrid model. So what needs tuning? So when you change resolution, you need to retune some of the emissions. So DMS, sea salt, and dust all need retuning when we drop to N48. You also, when you change the aspect ratio of your clouds, there's a cloud parameter that needs changing. Also, the amount of nitrogen that's produced through lightning, there's also a parameter there that needs tuning. Now, to tune it, we've been running these AMIP runs for 35 years. Now, here we've got some CMM plots. So the x-axis in all these plots, so all these are global averages, and the x-axis on all these plots is just the 35 years we've run the models for. So if we look at the top left, so the blue line is the standalone N96, and that's what we'd like our hybrid to match. The other two lines belong to a hybrid model. So the green line is our senior N96, and our purple line is our junior N48. So if we look at the top left, we've got surface temperature, and you can see that the lines all match quite well there. If we look at outgoing long wave radiation, then we can see that the N96 senior matches quite well to the standalone, but there's a bit of an offset to the junior, but we haven't actually retuned this cloud parameter yet. So hopefully that offset will become a bit less when we've done that. On the right-hand side, we've got, I can't see because it's covering, but I think it's moisture at 51 kilometer. And here we find that senior and junior map perfectly. So the green line has actually been overwritten by the purple line. If we go down to the bottom left, then we've got aerosol optical depth. Here we find senior and junior match quite well, and there's a bit of an offset to the standalone, but it is a fairly small offset. Bottom middle is cloud area fraction, and we find again that the N96 models match each other quite well, but there's a bit of an offset to junior. So junior is a few % less cloud area fraction. If we get to precipitation on the bottom right, then we can see that we've got the precipitation is a few % higher in junior. Can I go to the next slide, please, Hazel? Okay, so we've done a chemistry evaluation on these runs. So because we're not running UKCA in senior, we don't have any plots for senior. So now we're just comparing our standalone N96, which is the plots on the top, with the N48 Jnr, which is the plots on the bottom. Now, if we look at the left-hand side, then here we've got the nitrogen produced through lightning. And as I say, we can tune this so that the actual totals match quite well. But if you look at these two plots, I think you can see that they spatially match quite well. And if you look at the bottom plot, you can see, I think that it's a lower resolution than the top plot. If you look at the middle, we've got tropospheric ozone column, and that matches quite well. If we come to the right-hand plot, then we've got OX net chemical production. If you look at the numbers for OX production and OX loss, then they actually match quite well between the standalone and the hybrids. If we come to STE, so STE is the stratosphere-troposphere exchange, which is effectively the amount of tropopause, amount of ozone that has passed across the tropopause, then it's quite a bit higher in the junior model, and we're just sort of checking whether that is okay or not. But generally, we're fairly pleased with the performance of the hybrid model, and assuming we still are when we've looked at a few things in more detail, then we'll start running sort of pre-industrial control runs and historical runs. Yeah, that's me. Thanks.
All right, hi everyone. I'm just going to do a quick update on UKESM 1 with the interactive ice sheets. This is going to be very quick. There's a lot of interesting science, but that'll come in the talks tomorrow. So this is a version of the model that we've got. We're mostly interested in what it can tell us about sea level, and there's some interesting physics and feedbacks between the climate and the ice sheets. They're not a standard part of most UKESM models. They're a special configuration that you can run. Works with the adaptive mesh bicycles ice sheet model, and we're still, as far as we know, the only CMIP6 Earth system model that can do an interactive Antarctica. This is very challenging. There's a number of compromises in how we model the science that we do, but it's generally very successful. We like the results, and there's a model description appearing very soon in James coming up. So what have we done? We've done a bunch of Greenland only simulations that have been around for a couple of years now. We've talked about those at previous GAs. Vicky's going to talk about more about those tomorrow. The state of those is that they're done. The data is being summarized, and that's going to go up on the ESGF because that was done under the kind of ISMIP6, CMIP6 stuff. Newer since last year, we've completed our 4-member ensemble of scenario simulations with both ice sheets interactive. So we've got an extreme SSP5 and a kind of baseline SSP1 simulation there. 4 members sampling across ocean initial condition variability. Again, a lot of interesting stuff in there. That's where the plot on the bottom there comes from. I'm not going to talk about that. Anthony will tell you about some of the science there tomorrow. So what are we doing this extension year? So we're extending some of these runs beyond 2100, again with the extreme climate change scenario, really to look at the longer timescale commitments and implications. And we've got a run where we've cut out that forcing as well, so we can start to look at some of these ideas about ice sheet commitment and whether we've made irreversible changes. And that's something we're going to pursue as we go forward into kind of the next stage of UKESM and this 5-year proposal that Colin's going to talk about. We've also been progressing on making these a more standardized part of UKESM suites so that anyone who wants to can just click a button in the configuration and have their ice sheets running. I think that's what I've got to say.
Good morning, everybody. My name is Jeremy Walton. I'm giving you a quick update on how our data from our ScenarioMIP future projections run using UKESM 1, how that's getting over to the Earth System Grid Federation. So from this table, you can see that we have of the order of 32,000 data sets from these future projections currently available on ESGF. A data set here, I've defined it at the bottom as a variable, for example, the near surface temperature on a MIP table, for example, monthly, using a model. Well, obviously here it's UKESM 1, there is no other model that you should be using. For a variant like R1 in an experiment like SSP 119, and the way in which those 30,000 data sets are divided up between the different experiments, the different SSPs for the ScenarioMIP are shown in the table there. And also the number of variants that we have for those experiments. We've got at least 5 variants for each experiment. In some cases, we have go up to 19 different variants for a very, well, comparatively large ensemble. And a headline here is that since our last meeting, SSP 245 now has 19 variants, and that's been done as a byproduct of some work we did on something called COVID-MIP, which I'll be talking about tomorrow. So 32,000 different data sets available for you to use from our scenario runs on ESGF. Inevitably, however, that variable or that MIP or that SSP that you want is not there. Oh dear, what can we do? Next slide, please, Hazel. what we're doing at the moment is adding more data sets to that list, but now on a bespoke basis. So this really means somebody contacting us and saying, oh, could you do extra aerosol figures for variables for IPCC chapter figures, for example. Dust variables, in this case, we added them for HM3 as well as UKESM 1. Recently, I've been adding, producing extra variables for the Cordex experiment. So these are very large data sets. They're multi-level sub-daily variables, so they take up a lot of space. So they weren't included in the original runs of the experiments, and so because those were required for Cordex, I actually reran the 3 members of the SSP 370 and the SSP 245 experiments, and I'm currently processing those variables, and they'll go up on ESGF for like the AMIP people to use. And then various other lifetime variables. So these are just examples of the sorts of things that people have asked us for to add to those data sets that are already on ESGF. And I am shortly to start the processing of the output from UKESM 1.1, which Jane has been talking about this morning. So there'll be the variables from the historical experiments, SSP 126, SSP 370. There'll be 6 members from each of those experiments there. So there we are. That's just a quick snapshot of what is happening as regards the scenario future projection variables generated by UKESM, currently available on ESGF. Thanks very much indeed.
Morning, everyone. I'm going to give you a very quick update on ESMVal tool. And this is on behalf of Ranjini, Lee, and myself. ESMVal tool being a scientific software package, there's a 3-pronged approach to its development. It's obviously the technical development. We are currently at version stable 2.2.0, and we're releasing 2.3 this month. We've integrated the functionality, which is the latest version, and it's a major change from Iris 2. Contains a whole bunch of upgrades and not so backwards compatible changes. We've deployed ESMVal tool as a package on Conda Forge and Docker Hub, and obviously PyPy and the old ESMVal group Conda Cello. We have implemented strong testing capabilities, including Circle continuous integration and GitHub Actions. So this helps us in our development process. And we have deployed it as central installation on Jasmine and DKRZ, and hopefully in the future it's going to be on the BSC cluster as well. So this was technical. Then the scientific progress, obviously, we rely on the scientists to contribute diagnostics in here. We have had quite a few within the time frame between the major release 2.0 and the current one, 2.2.0. There has been a lot of progress with porting existing metrics from other packages like AutoSES. And this is part of a whole bunch of other projects like EasyNess Tree, for instance. And the IPCC AR6 chapter developers have contributed heavily. We are in the middle of the, we have just started the process of moving all those diagnostics that the IPCC developers have written and moving them. Starting to move them onto the master branch so that they will be available for next IPCC round of analysis. Primavera metrics and more observational processing capabilities, as in integrating summarization of observational data. We've had good contributions from the ESA CCI people and as Met Office, as a few Met Office people. Very important.
1 minute.
Sorry?
1 minute.
Oh, yeah, I'm there. Very important user engagement. We have We have a dedicated using engagement team, which is led by Ranjini. When we have all sorts of support for users, including dedicated tutorials, GitHub discussions, GitHub issues, and all these things. And I put a whole bunch of resources on the right-hand side. And there's a plot by our own Jeremy Walton showing the near surface temperature anomaly. And it goes to show that even complete newbies in ESMBL2 can produce nice and attractive and scientifically laden plots. That's me. Cheers.
Okay, right, back to myself, Colin, just to finish. This is just to say one or two quick words on UKESM2, which is the future. Okay, next slide, Hazel, please. This gives you both the timeline and the primary things that look like they'll be going into UKESM2. It's not a closed shop yet, but as I'll say, it's a shop that doesn't have as many workers as it used to have, and it's open half the time it used to be, so we're under a little bit of pressure. So UKESM2 will be built on HADGEM3 GC5, which is the physical model coming next in the MetalFist development cycle. It should be available to us in the spring of 2022 to start using, but it won't be in its frozen full version till the end of 2022. We're aiming, therefore, to have a UKESM2 ready to use by the beginning of 2025. The target development, so we're going to keep it the same resolution, but we hope to be able to use the hybrid approach that Mark talked about to have a higher resolution one, maybe N216, N96, and or quarter ocean. Some of the things we're adding in, so it will be able to run with the emissions of both CO2 and CH4, which Gerd Folberth and Fiona O'Connor and Chris have been spending a lot of time working on. And some portion of the nitrogen cycle will also be fully interactive. So those will be closed cycles of CO2 and CH4. Then we'll try and make the interactive Greenland and Antarctic ice sheets more standard in the model. Wildfires are being implemented. They're largely there already, connected to the carbon cycle, terrestrial carbon cycle, and to atmospheric composition. And a few other things that we are hoping will be included. And I've even got one that is not, that I'll tell you about. Thermal acclimation of plant photosynthesis, some improvements to the treatment of land use, a representation of nitrate aerosol, some improvements to stratospheric ozone, possibly switching from the bin dust scheme to the modal treatment of dust. And the one that I've got missing is we are thinking of having an increased number of soil layers and improved soil physics, mainly to support permafrost work. So that's hopeful that will be in. As a step along the way, we're developing an emission-driven version of UKESM 1.1. Next slide. So now just a few caveats. So we're aiming for early 2025 now, not end of 2024. We think this fits with a probable CMIP 7 schedule. We'll continue to try and maximize couplings, prognostic couplings, to allow us to look at feedbacks as much as possible. Just to note, this almost definitely will be the last UM-based UKESM model. We will start interacting more with component model developers after the summer. We hope and we expect that GC5 will have a better historical performance than GC 3.1 and UKESM 1. There is a MetOffice historical PEG, process evaluation group, that is working to try and ensure that there is a good historical performance for ideally the right reasons. It doesn't necessarily mean it will be a lower climate sensitivity, but it probably does. Next slide, and I think that's the last one. Last things to note, while we're starting from more knowledge than previously, we have less time, possibly half the amount of time, and we have less people in the team that are funded to do this. So we learned in UKESM 1 that we need to be quite hard on deadlines. We're going to need to be even harder this time. We need to ensure that anything that's coming in is well tested and is coming in early to have any chance of being in UKESM 2. And I guess the last point is the bottom line. We really need to take a pragmatic approach to UKESM 2, as the person years and the sort of number of people and amount of time available to do this is severely restricted compared to UKESM 1. And I was going to tell you a little bit about terra firma, but we've punted that into the next session with one slide, so I think I'm done. If you check for another slide, I don't think there is one.
No, that's the end.
Yeah,
Over to
which
Q&A
means
now.
I think we can probably switch to Ranjini for 5 or 10 minutes.
Right. Colin, since your mic's open, I'll go with you. So quite a few of the questions asked in the chat have been answered by the speakers. So I'm just going to try and cover the ones that haven't been answered. So Yevni asks if what the plans are, if any, to account for the subsea permafrost methane.
Yeah, so in UKESM 2, I think the plans are that we don't have any. I think that's still something that's being investigated offline in ocean-only configurations. There's nothing that is sufficiently mature for us to take over.
Right. Doug makes a comment saying that the layered soils may also help with some of the Amazon dry biases we're having. And there's one.
Yeah, agreed.
There's another quick question from Adrian to ask if any sign of degrad being available to allow marine BGC at low resolutions.
Yeah, so degrad is the online coarsening. So it is still alive and it is still progressing. It's going slower than it was. There is some potential, I think, but it will not happen in the next year or two. You might want to ask Mark Stringer a bit more offline. He may be more updated than me. Right,
and Yevni just writes a note saying that he would take this conversation up about subsea permafrost methane offline with you as well. I'm going to come back to your first session. There was a question from Chris Jones on the LTSM-1 extension plans. He asks if RA1 will also look at uncertainty in forcing datasets.
So it certainly should look at uncertainty in observational datasets, and that's something I think the NCO have some background in. So, but you're right, we could also look at uncertainty in forcing datasets. So I think there is a forcing MIP, isn't there, that's starting. So it's a good point, and it's one that we should consider. Yeah, I think we would be pushing the uncertainty of some of the forcing datasets too far to explain some of the warming we have in the end of the historical period. But certainly, yeah, as you say, the study that NCAR did with biomass burning was an interesting one. Yeah. So without doubt, and I think that particular one, Jane, is actually running experiments with UKESM-1 to try and replicate some of their findings. So you could talk to Jane about that. But I agree. Yeah.
And then there's just one question for Jane. It's kind of a part question, part comment from Rich Allen. Jane, have you looked at the AMIP experiments for more consistent comparison to satellite observations? And he has cited a paper there, and I can forward that to you if you haven't already got it on chat. Jane.
Super, yeah. So obviously the initial some of the initial evaluation plots, at least on the atmosphere aerosol side there, was looking at the fully coupled setup. We certainly have the AMIP to do more detailed evaluation activities like that. So I think that's probably a good way forward. So I was hoping again in this afternoon's breakout group on the evaluation that we can discuss, you know, what further kind of evaluation activities like that, and where particularly NCO can get involved. Definitely there's more room for more activities there, I think. So yeah, I think that's one that we can maybe discuss in more detail this afternoon, but it's a good point. Thanks.
All right, I think that's it with all the questions that have to be answered. Everything else has been taken care of in the chat, and I see, you know, thanks to everything, I mean, you know, in response as well from the people who asked the questions. So I'm guessing that it's either satisfactorily answered or you will be taking these conversations offline. Mark has a final note on degrad as well yeah, so I think that was in response to Adrian's question. So surprisingly for us, we finished 6 minutes ahead of schedule. So I'm going to hand over to to Hazel, unless anyone else has any pressing questions. Right, over to you, Hazel.
I'm just going to quickly jump in.
Sure.
I'm going to quickly jump in if that's okay, given that we've got the moment. So after the break, we've got we're going to introduce a little bit of a plenary breakout group, and that's to discuss these potential 2 workshops on one with the impacts community and one with the climate policy community. So just to say, when you go away for your coffee, have a think about, particularly if you know of any impacts groups in the UK or impact related work in the UK that we should be interacting with. And likewise, beyond the obvious policy people at the departments of BEIS, DEFRA and Foreign Commonwealth and Development Office, if there's any other areas that you think we should be interacting with, it would be helpful to hear those in the discussion. So having pushed people to go a bit quickly, we may now have a little bit of time. So Hazel, do we have anything else, or should we just go to an early coffee break?
The only other thing you could cover is terra firma now, or you could do that after coffee.
The one slide that we have, you mean? Yeah, why not? If you can go forward with that slide, we can do it now if you like. We had thought we'd talk about terra firma afterwards. So some of you, I think most of you know that we've written a proposal for what you might call a second UKESM project, but it is not a model development project. It's far more about using UKESM model capabilities to do science. So that project is called Terra Firma, Future Impacts, Risks and Mitigation Actions. And we were going to use it a little bit in the follow-up discussion, because we thought some of what we proposed there in terms of simulations and interacting with different government departments to devise those simulations could be a useful use of the one-year extension workshop that we proposed with those communities. But as a reminder, in case you need reminding, so terra firma has 6 work packages, and they're shown in that little box there. It has a work package that organizes the model simulations and observations. And 2 of the main sets of simulations are, one, we're going to try and run some what we call temperature overshoot simulations, where global mean temperatures exceed a certain amount, say 2 degrees, maybe raised to 3 degrees, and then are brought back magically to 2 degrees afterwards through some kind of magical removal of CO2 from the atmosphere. So we're going to do those experiments to be able to look in work package 4 and 5 at what might happen to rapid or irreversible change in the Earth system as a function of these overshoot scenarios, and also look at some societal impacts associated with those overshoots and how they compare to cooler global mean temperatures, and also if impacts are reversible. And as you know, under the rapid and irreversible change, we are emphasizing the Antarctic ice sheet, marine biogeochemical and ecosystems, and tropical forests. And under the societal impacts, we're looking at water resources, fires, climate and air quality, global sea level, and marine biogeochemistry again. And then we have work package 2, which is on developing some approaches to mitigation experiments, either looking at near-term climate forces such as methane and tropospheric ozone, and or land use, which is work package 3, land use as a mitigation option. And within work package 3, we're also looking more at the carbon cycle, because it plays clearly an important role if you want to do something with land use and mitigation. Work package 4 I mentioned was about rapid or irreversible change, and work package 5 is about impacts, societal impacts, and I mentioned what those were. And then finally, work package 6 is a knowledge integration and science communication activity, where we're trying to communicate with lots of the groups that are mentioned around in the outer circle, our stakeholder group. I should say that the terra firma is a NERC funded project, but the Met Office Hadley Centre is strongly involved and has sort of aligned 10 FTE, 7 of which are the core group members, to work closely with us on all the activities that are going on in terra firma. So whilst terra firma by name is a NERC funded project, it will interact very strongly with the Met Office Hadley Centre Climate Programme. And that's primarily with the ESMS team that Andy Wiltshire heads, that Chris used to run in the past. So we look forward to that. And I have now successfully utilised the few minutes spare we had.